Welcome back to our statistic learning session. Today we'll be talking some more about examples since last time. And last time we talked about Faircoin example. Today we'll be talking about news on YouTube example. In this example, we are talking about a one-sided test. In last example, we talked about two-sided test. So do you guys remember the YouTube example? In this example, we surveyed around 5,000 people and asked them about who are taking at least some of the news from YouTube. The answer we got was 32% of them said they were taking their part of the news from YouTube. Now, what we're asking here is 32% significantly smaller than one third? That's what we're asking. We have one third value in one hand, and we're asking whether the people who are taking news, is it significantly less than one third? So this is the test. Here we have hypothesis. One is null hypothesis, which says that people who are American people who take more than 30% of their news from YouTube. That's a null hypothesis, but alternative hypothesis is less than 33%, less than 30% of the people take their news from YouTube. And again, this is a one-sided test. This is a one-sided test. Now, we have a reject condition, which is called TN, and this is we will reject if this is true. If this is true, then we will reject it. Now, in this clause, should I put the absolute value around this expression? No, correct. Because if you put this value around this expression, then it will become a two-sided test. But we are not interested in two-sided test. We are interested only in one-sided test. Therefore, the Tn will be equal to like this. The Tn, which is a test statistics, will not be an absolute value for the one-sided test. It will be like this. It will not be a one-sided test. And why we are doing one-sided? Why we are not doing two-sided here? Can you guess? We are doing one-sided because we are not concerned about whether the we are not asking that whether the American people we are not concerned about we are not asking whether one third American people, average American people see more than 33%. We are only concerned about less than 33%. That's why we are only concerned about one-sided test here. and we'll reject the null hypothesis if this is true. If square root of n Pn minus P and square root of P 1 minus P is greater than some C, and we'll decide on what value of C is later. Okay, let's try to decide what a value of C is now. Well, to do that, we have to understand our rejection range. What is our rejection range? Our rejection range is 0 through to something less than 0.33. And what is our null range? Error not is anything greater or equal to 33 to 1. So this is our, there are two values here, 0, 3, 2, 1, and 0, 2, something that's less than 0.33. That's our Theta naught and Theta 1. Now we still haven't decided what a value of C is. For a starter, what we can do is we can say that the value of C is a Q naught. By definition by definition, the value of C is always a Q naught here. But we still don't know what the value of Q naught is. Q alpha is. What should be the value of Q alpha here? Now let me write a function that will help us to understand what value of Q alpha should be. Besides the point, we know the value of Q alpha, but at this point, what is the value of the P should be here? What is the value of P should be here at this point? That's the question. If our test, to run our test, it has to be something within the P naught, isn't it? If this is something within P naught, then it has to be value within 0.332, 1. It has to be that value. But we have to choose P in such a way that P is, this condition holds true not only for a particular value of P we choose, but all the values for a P that comes within Theta naught. What kind of value of P would that be? Can you guess? Let me write a new definition for this so that it helps us to define, crystallize what I'm trying to say. What we are trying to do is we are looking for a probability such that square root of n P hat P naught square root of P naught 1 minus P naught is greater than alpha. It is a function of P and P naught, and it has to be less. It will be less than alpha for all values of P which is greater or equal to 0.33. That's what we're trying to do here. We are looking at this equation, this expression, and we are looking at probability that this expression holds true, probably this is true is equal to some alpha, is less or equal to some alpha, and this P naught should be equal or greater than 0.33. For all this expression should hold true, and it should be equal to this probability for all the values of 0.33. What value it should be? If anybody who's reasonable will guess that it's 0.33. If it's true for 0.33, then it is true for all the values greater than 0.33. It is a baseline value. And if that is true, then everything above is also true. So therefore, we are choosing a value that is right at a boundary. So the value of P naught should be 0.33. We are choosing a value which is at a boundary and is likely to cause most of the confusion when deciding whether it is theta naught or theta. And that's why we are choosing a value that is right at a boundary. This is all good. How about different situation where theta and theta naught are not continuous? Let me give you an example. Let's say there's a line between 0 and 1, and there's an interval 0.5 to 0.6, which is a theta naught. And this is theta 1 and this is theta 1. They combine, both become theta 1. And the remaining is theta 1. How do we choose, or how do we do the hypothesis testing here? So let's say H naught is P belongs to 0.5, 0.6, and H alternate hypothesis it doesn't belong to 0.5, 0.6. How do we do that? How do we know which one is the correct boundary? For that, we have to calculate the individual type 1 error using 0.5 and 0.6, and whichever gives us highest type 1 error, whether it's 0.5 or 0.6, is the right boundary for us. Moving on. Now let's do some exercise. Let's take a same example where we have H naught as P, which is less or equal to 0.33, and alternate hypothesis is if P is greater than 0.33. Now we'll use a common sense way to come up with an expression that would give us C. We'll say that P hat is equal to average of xn is greater than some alpha. We don't know why. We don't know what it is, but it is alpha right now. We'll decide it later. But this is actually 0.33. But just for sake of in theoreticalness, we'll decide later. And we'll take supremum of probability of P such that where P is less than 0.33, xn bar is greater than alpha. When n goes to infinity, is tends to go to alpha. What he's saying is that probability of xn bar that is greater than certain value alpha tends to become then lambda tends to become alpha when n goes to infinity. That's what it's saying. Now we don't know what alpha is here, but right now, for that reason, we'll use central limit theorem to do some standardization here or normalization here. Again, doing SGP, which is P P1 minus P is greater or equal to, it has to, since we are subtracting and subtracting the minus P from one side, it has to be done for both sides because there is inequality. So that's why we need to do on both sides. P1 minus P, and still it tends to alpha. So this alpha, this expression is equal to C. And C here is, what is C? It is Q alpha. You should be able to, which is equal to 1.645 in this case, because it's a one-sided test, which is equal to 1.645. And lambda here is 0.33. Now, what is the value of this? What is the value of this expression here? What is the value of this expression? We know lambda is 1.645, but what is the value of this expression? The value of this expression is we have earlier. Let me see. It must be now on the slides here. Let me just tell you from the other slide. It is minus 1.5. The value of this is minus 1.5, and C is minus 1.645, which is true. So therefore, we will not be rejecting null hypothesis. Therefore, null hypothesis must be true. That means the P is rather greater than 30% of people who watch YouTube to get their news. So that's for today. That's all for today. Let me quickly summarize what we discussed today. We discussed about news on YouTube. Null hypothesis was more than 30% of people get their news from YouTube, while alternative hypothesis was less than 30% of people get the news from YouTube. We use the central limit theorem to do our one-sided test to see whether if this is which hypothesis is true. If you can reject the null hypothesis that people see more than 30% of their news on YouTube, and by doing some calculation, we will not able to reject it. We did our test at 5% at asymptotic level, and our result was that we cannot reject the null hypothesis. So that's all for today. I will see you next learning session. Thank you so much.